Let us discuss about the you know qualitative molecular orbitals diagram of actually for Metallocene. Okay, so today we're going to discuss about the qualitative molecular orbital diagram for Metallocenes. So molecular orbital diagram means we are going to talking about the molecular orbitals which are formed between the ligand group orbitals of the ligands and the atomic orbitals of the metal. Okay, and also their energies, because this is all related to the energy diagram, so we have to talking about the energy. So already we know that we have the symmetries for the metal orbitals and for the ligand group orbitals. In the previous class, last class actually, we already discussed about this ones. And for metal orbitals we get the symmetries like A1Z, E1Z, E2Z, and A1Z again, E2U, A1U. Okay, so we get the symmetries for metal atomic orbitals, and it is actually shown in the this one. Okay, these orbitals represent the symmetries of the metal. Here it is, you see, metal orbitals, and this is also here indicate the metal. Okay, so similarly we have also ligand group orbitals, which are formed from the combinations of the ligand molecular orbitals. Okay, we already discussed this in detail in the last class. Okay, so here we have also A1Z, A2U, E1Z, E1U. Actually, this is not A1U. Okay, this is the E1U. Okay, this would be, and here it is your E1U and E2Z and E2U. So if you notice here, then here is A1Z is present here, and here also A1Z is present. Okay, and E1Z is here present, here E1Z is present, E2Z is present here also present. Okay, so A1Z again here, this one same thing, and this E2U here, one E2 is present, and here E2U, no, actually no E2 is there, no? A1Z, then A2U. This is not E2U, this is A2U. Okay, this is A2U. So that means let's suppose this one is your A2U. So A2U present here, and also the A2U is present here. Okay, so E1U is present here, and U is present here. Okay, so the left, this one is not present. So that means the in ligand group orbitals we observe that E2U is present, but in atomic orbitals of the metal E2U is not present. So that means this will going to remain as non-bonding. Okay, so this is going to remain as a non-bonding orbitals. Okay, so coming to the actually we already know that on concept of overlapping. So overlapping will going to give you what? Overlapping will going to give you the bonds, no? So to form a bonds, the atomic orbitals must overlap. and we have the idea that to overlap there are three conditions are there, no? The first one is your the energy of the atomic orbitals, in this case atomic orbitals of metal and ligand orbitals of the two ligands, no? So energy should be similar. Okay, similar means this they have equivalent amount of energy they must have. Okay, second one is your symmetry must be same. Okay, symmetry must be same. And third one is your orientation. Okay, so this one actually this one is already we already discussed this one, and we get the symmetries now for the metal and the ligand group orbitals. Okay, so what about the energy? So we can calculate the energies of all the symmetry elements or the orbitals by using one analytical technique which is known as photoelectron spectroscopy. Okay, photoelectron spectroscopy. Okay, so photoelectron spectroscopy, by using this one we can calculate the energies of these orbitals. Okay, and actually the symmetry of elements. Okay. So once we have the energy of this one, then we can draw draw the molecular orbital energy diagram, because you see here in case of ligand group orbitals, actually by using the photoelectron spectroscopy they found that the energy of this A1G and A2U are same. Okay, and they have the lowest amount of energy among these orbitals. Okay, so it is actually shown here. That's why their energy of A1G, so this one is okay, so A1G and A2U are same and they have the lowest energy. And the next one is your this one, E1G and E2U. So this one is for this one. Okay, so they calculate the energy by using the photoelectron spectroscopy, and and similarly they also they did these things for all the orbitals, and they just draw the energy diagram level by using two lines or some lines as shown in this figure. Okay, as shown in this figure. So we have this now we have the the molecular orbital diagram. So now we have this one. Okay, this diagram we have. So from this diagram, what we can interpret it, or what we can what knowledge we can gain from this molecular orbital diagram. So first of all, we have this energies and we have this energy. Okay. Understand? So now what we can do, we can see the combinations, and we can even see the possibility of formation of bonding. Okay, so mainly what we are talking about the bond, this one, no? We are talking about this ferrocene, no? So this is also for other metallocenes. Okay, mainly we are actually discussing about this one. So molecular orbital is also okay. So please remember, this molecular orbital is for ferrocene as well as the other metallocenes. Okay. So actually we are discussing about this one. So that means we are talking about we are trying to find out the molecular orbital. That means the bond between this metal and the ligands. Okay, so these bonds basically talking about this bond, iron, that means this metal to ligand, this bond, this bond and this bond, this bond and this bond. Okay, so which orbital is going to stabilize this bond, and how are you going to know that which will going to contribute to the stability of this bond? So for that we have to just go to the molecular orbitals. Okay, and molecular orbital energy diagram. And if you zoom this one, let's suppose, okay, here, okay, so you have this one now. So now if you notice here that, one minute, okay, so now you see that this A1Z, okay, so this A1Z of ligand group orbitals, and here A1Z is where is this one in d orbitals. Okay, so we have A1Z in also d orbitals of metal. Okay, but if you see the difference of energy, so the difference of energy between these two symmetry elements are considerably high. Okay, so this is very significant amount of energy difference. So that means they will not going to overlap properly, though they have the same symmetry. Okay, they have the same symmetry. Okay, so we already know that the three conditions, energy should be similar. Okay, only symmetry will not going to tell you whether the pole is strong or not, because the symmetry will only going to tells you that the overlap is possible or not. It is possible, but what is the strength of bond? The strength of bond will be depends upon all the three factors. Okay, so here the energy of the ligand group orbitals of the A1Z is quite different. They have different amount of energy, and the difference is significant. So that means they are not going to give a strong bond. That means the stability of this bond is not coming from this overlap. Okay, so that means the A1Z, when we are talking about A1Z, that means this is related to what? This is same symmetry as s orbital. So s orbital is related to what? Sigma bond. So that means the ligand group orbital or ligand A1Z is not as good sigma donor. So what we can say that the ligand A1Z is not what? Not a good sigma donor. This is poor, we can say poor sigma donor. Okay, so ligand A1Z is a poor sigma donor. Okay, similarly, if you notice A2U, so if you notice A2U, and here A2 is present here, this one A2U, actually A2U is not present here, so this will not going to, here no A2U is present, so this will remain what as no A2 is, no A2 is not present, so that means they will going to remain as a non-bonding or actually A2U is present here. You see, A2 is present here. Okay, but this the the amount of the difference of the energy is very high. Very high. So actually, they also not going to contribute to the stability of the metal and ligand both. Similarly, we can also say that E1U and E2Z also not going to contribute, because if you consider E1U, then E1U is the energy here and E1U is energy actually this one. Okay, this is actually E1U, okay, not A1U. It is mistake. Okay, so here the energy is considerably high. Here also you see E2Z, and here it is E2Z. So these energies are also considerably high. So they also not going to contribute to the stability of the metal and ligand bond. Okay, so that means actually this E1Z, okay, this E1Z, this E1Z and this E1Z only going to contribute to the, because they have a slightly lower difference of energy. Okay, they have a slightly lower difference of energy in compared to the others. and this energy is not so significant. that, that means the difference of this and the difference is not so significant. So we can say that the stability of this bond, that means this bond, okay, this bond is, that means this metal ligand bond is mainly due to the E1G symmetry. Okay, I think hope you understand up to this one. Okay. So what we can conclude? We can conclude from this energy level diagram. Not this is the one conclusion. Okay, the one conclusion is that the stability of the metal and ligand bond is mainly because of or the contribution of E1G. Please remember this point. Okay. Now coming to some examples of Metallocene. We have already discussed about it is complex now, the ferrocene. Here the number of electrons will be what? If you count the 18 electron rule, then by using normally this is neutral atom method, no? So iron is 8 plus 8 electron can be contributed from iron, and here cyclopentadiene 2 cyclopentadiene 5 into 2 is equal to 18. So that means this complex, that means cyclopentadiene complex is stable according to your 18 electrons rule. Okay, so 18 electrons rule, this is stable. So if you come to this Metallocene example, then it will give you 19 and this will going to give you the 20 electron. So that means these two are slightly actually this is slightly not stable than this one. Okay, so how are we going to justify this stability or understand this stability of the iron, which is more stable than these two? So we can use even this the molecular orbital. You can use this molecular orbital diagram. So here you see, here you have how many in this red lines, actually this red from here to here, this red molecular orbitals represents the bonding molecular orbitals. So how many bonding molecular orbitals are present? 1, 2, 3, 4, 5, 6, 7, 8, total 9. Okay, so we have 9 bonding molecular orbitals. Okay, so 9 bonding molecular orbitals, so 18 electrons can be there. So in case of and here the green lines represents your anti-bonding molecular orbitals. Okay, so we know that if some electrons will be in the anti-bonding molecular orbital, that means that complex will be not a stable complex, they are destabilized, no? And the electron which are present in that anti-bonding molecular orbitals can be easily removed, and that's why they going to react faster than the one which have only bonding molecular orbitals. Okay, so in case of this ferrocenes, they have only 18 electrons, so they can only they can be only in the bonding molecular orbital, because only 9 bonding molecular orbitals are present, and 18 electrons can easily fill the all 9 bonding molecular orbitals. Understand? Again, in case of in case of your this one, this complex, not cobalt complex. Okay, here 1 electron is extra, no? And that 1 electron can be in this anti-bonding molecular orbitals. Okay, so that means these electrons are available for reactions, or this electron can easily we can remove this electron easily, or these electrons actually destabilize this complex, because stability is coming from only that electrons. Okay, not stability, reactivity is coming from that electrons only. Okay, so similarly here also 2 electrons will be in that E1G orbitals, which are your antibodies. So that means we can use these molecular orbital diagrams even to understand the stability of different complexes. Okay, different metallocenes.